Alright guys, so a couple of days ago we talked about single replacement reactions in which one element replaces another element that's within a compound. But today we're going to move on and instead talk about double replacement reactions. Alright, so in double replacement reactions, what happens is that we have two compounds coming together and they swap elements. So here, kind of in this picture right here, and I marked out the dis because sometimes people will call it double displacement, but for our purposes we'll just keep saying replacement. So what happens is these two compounds are going to swap elements to create two new compounds. So this is kind of the general format where you see a swap between elements in a compound. So what we're going to do today, kind of using your guided notes, is go over the kind of three subtypes of double replacement reactions. And I'm just going to run through them pretty quickly, so if you feel like you need to pause the video to write some things down, please feel free to do so. And this information can also be found in section 8.2. So if you need to go there for more information, then that's totally fine as well. Alright, so the first type of double replacement reaction that we're going to talk about is when two ionic compounds come together. So the first thing that's important to realize about this is what happens to ionic compounds when they're placed in water. Because when these compounds are mixed, they're going to be in solution. In other words, dissolved in water. So what happens when we have an ionic compound, otherwise known as a salt? So it comes in as a solid, but once it's in the water, it's going to split apart into its ions. So potassium bromide will split into K plus and Br minus, and then silver nitrate split into Ag plus and NO3 minus. So, once those ions are in solution, they're free to recombine with each other. So now we can have bromine combine with silver and potassium combine with nitrate. And those are going to be the products of our double replacement reaction. So let's go ahead and write out those products. So we know in double replacement, we have two ions that are going to swap places. So Br is going to trade places with nitrate, and nitrate will come over and be a part of the compound with potassium. So let's write our new balanced products. So if K is plus 1 and NO3 is minus 1, then they'll come together in a 1-to-1 ratio. So one of our new products will be KNO3. Now for our other one, if silver is a plus 1 and bromine is a negative 1, again those are just ionic charges based on the periodic table, the new compound that will form for them will also be in a 1-to-1 ratio, AgBr. And if we check to see if it were balanced, it is, so that's great. So now, the next thing we have to do is to decide if, when these ions recombine kind of in solution, if they stay ions or if they come together to form a solid compound that we call a precipitate. And so in order to determine what happens, we're going to have to check our solubility rules on our reference sheet. Alright. So here are our solubility rules on our reference sheet, and what they're going to tell us is if a compound remains in ion form, if that's the case, it'll say soluble, or SOL, okay? But if we see PPT in the square corresponding to our compound, then that means it will fall out of solution as a solid precipitate. So the way this chart is organized is here on the left, that's where you have your anions, and here on the top is where we have our cations. So what we'll do is, looking at our first compound, our anion is nitrate, so that will put us in the first box here, while our cation is potassium, so that will put us here because potassium is an alkali metal. So if we kind of trace these together and see where they end up, that's going to put us in a box where the rule is soluble. So what that means is that these potassium and nitrate ions will remain ions when combined in solution. And so how we're going to note that is by adding in the state and saying that potassium nitrate will be aqueous. So here it is important to add the state. So now let's go in and do the exact same thing for silver bromide. So if we look at bromine, here it is in the third box. And then if we go and find silver, here it is in the second column, and kind of trace where they come together, what we see is that this compound will form a precipitate. So that means that it will come together as a new ionic compound that's in the solid state, so it'll fall out of solution. And how we're going to note that is by putting the solid state right after silver bromine, or silver bromide. So when dealing with this first kind of double replacement reaction, we're always going to need to check the solubility rules. So now let's do another example. Alright, so here's our second example of when two ionic compounds come together. So we know that in a double replacement reaction, we're going to have two of the ions swap places. So let's go ahead and predict what our new ionic compounds will be. Alright, so now mercury is going to be paired with nitrate. So if mercury here is 2+ and nitrate is -1, we're going to need 2 nitrates per every 1 mercury. Now, since ammonium is going to be paired with sulfate, and we see ammonium has a +1 charge and sulfate has a 2- charge, we're going to need 2 ammoniums per every 1 sulfate. Alright, so now that we have our products, let's go in and check our solubility rules. So here we have mercury pairing with a nitrate, so when we kind of trace those together, we'll see that this new product should still be soluble, so it'll be in the aqueous state still. Now, if we do the same thing for our second product, where we have ammonium and a sulfate, what we notice is that this product will still be soluble as well. So we'll write the aqueous state for both. They'll still be ions dissolved in solution. So whenever this happens, what this means in terms of our reaction is that the reaction does not occur because there's no precipitate. So what you'll do is still show your products. You'll just want to show where both are in the aqueous state, and then underneath it you can write no reaction. Alright, so now let's move on to talk about the second subtype of double replacement reactions. Alright, so the second type is called acid-base neutralization, and that's where we bring an acid and a hydroxide base together. So again, what you look for in an acid is it needs to have hydrogen at the front, and for our base here, when we say it's a hydroxide base, it needs to have the hydroxide ion at the end. So that's what we're looking for. So now, as typical of a double replacement, let's go ahead and predict the products by swapping the ions. So, we know that chlorine and OH are going to change places. And so in doing that, what we're going to produce are water, because when we combine hydrogen and oxygen, that's what we get, water. And then we're also going to form a new ionic compound, or a new salt. So let's go ahead and write our new product of water. And then now let's write our new salt. So in our salt, our cation will be sodium with a +1 and chlorine that has a -1, so we just need to have them in a 1-to-1 ratio. Now the last step on these problems is to go in and make note that we're forming a brand new molecular compound. Molecular compounds are covalent, and we know that's true of water, right? It has two hydrogens covalently bonded to an oxygen. So what we're going to do to note that is underline the compound, and then we're going to add in the liquid state. So it won't be ions, it'll be a new compound, water, that's formed. And so whenever, again, you're doing this second type with acid and base, we'll always get water. You'll always get water in a new ionic compound. So here we have NaCl, a new salt. Alright, so now let's move on to cover the third subtype of double replacement reactions. Alright, so in our third type of double replacement reaction, we're going to be bringing together an ionic compound and an acid. So again, an ionic compound, you recognize it because it's a metal and a nonmetal, and an acid should have hydrogen at the beginning. So here this is hydrosulfuric acid combining with zinc chloride. So as is typical of our double replacement reactions, let's go ahead and swap the ions at the back and write our new compounds. So zinc is 2 plus and sulfur is 2 minus, so those will just combine in a 1-to-1 ratio. Then for our second compound, hydrogen is normally plus 1 and chlorine is normally minus 1, so those will come together to make our new acid, HCl. Okay, and so here is our new acid that's produced, and here is our new ionic compound. Alright, well those are the three subtypes of double replacement reactions.